Today we're going to go over free body diagrams. Free body diagrams are one of the most common things in any single physics or engineering classes. And most students don't actually struggle with the physics because it's hard. They struggle because they skip this one crucial step, and that is drawing free body diagrams. Today I'll show you the basics of how to draw it and what it actually is and how to use it to solve problems. So first things first, what are they? What are free body diagrams? So a free body diagram is a diagram of forces that a diagram that shows forces acting on an object. So either a block sliding down a ramp and has forces shown on it, or a boat on water. We can simplify the boat and visualize all the forces. This basically gets any system simplified and allows us to put it into formula form. But what constitutes as a force, right? So a force in free body diagrams, you should think of as interactions. What physically touches, pushes, pulls an object, right? If something is touching or pulling it, it's a force. If it's not, do not draw or put it on the free body diagram. All right, so let's get into the general method. So we're gonna go with kind of this example right here. This is a cross section of a cannon. Please ignore if you're an artist. This is a cannon cut in half so we could see the ball right here. And the ball, you have a little spark plug here. Once it blows up, the gunpowder here explodes, causing the cannonball to shoot out of the cannon. And my question is, I want to know all the forces acting on the cannonball right as the cannonball fires, right? This could be useful if I want to find, speed of the cannonball, or, will the cannonball even break, or will it actually fly out if I'm an engineer creating this. So let's draw a free body diagram just for the inner, this cannonball right here, as soon as the cannon fires. So first things first is you want to isolate what you're drawing. So in this case, we're looking at just this cannonball right here. And we're going to take that element and we're going to make it a square, just to simplify it. So this square, this element right here, that is the element of the cannonball, right? This is the element that we are looking at, the cannonball. So on this element, we need to draw forces or interactions, right? So let's look at what force is causing it. So we have a force that causes the cannonball to shoot to the right, right? We have the gunpowder. So I'm going to draw an arrow and call it F gunpowder, right? It physically touches the cannonball. It pushes the cannonball out to the right. We have the weight of the cannonball, right? The cannonball has mass, right? It is not massless. They're quite heavy, in fact. And weight is always pointing down. Weight we denote as W. We can also write force due to gravity. And this is also equal to mass times gravity, right? All of these say the same thing, but that is the weight of the object, in this case, the cannonball. Something to note is we always draw the element as a square and not any other shape, just because the square simplifies any system to have an up, down, right, left. If it's to an angle, we can just draw the square at an angle, which gives us this triangle theta, which we can solve better if than if it was a circle or any other shape. let's go back to the free body diagram here. So we have force of gunpowder to the right, we have weight force down. Um, but let's also think about, is anything slowing down the cannonball as it shoots out? We have friction within the barrel, right? It isn't a smooth surface. So we have friction opposing its motion. So I'm going to draw friction force. So F due to friction. That's the tiny f right there. And then we have another force called the normal force, that goes directly up. And normal force always is the force of the ground that the object is sitting on pushing up. So if I have a ball on a ground, right, the ball's weight pushes on the ground, but the ground also pushes back on the ball, and that is called your normal force, right? If your normal force and your weight, if the object is not moving, they are equal to each other, right? Due to Newton's second law. Um, so always include your normal force if your object is sitting or moving on something. And there you go. This is the free body diagram of the cannonball inside the cannon. All right, now let's try an example on your own. We have a man back here taking boxes out of a truck, and he places a box onto a ramp. The box starts sliding down this way. Draw a free body diagram for this block. Feel free to pause the video and try it on your own. I'm going to give you a few seconds, then I'm going to work it out. All right, hopefully you had a chance to solve it. If you need more time, please pause, but I'm going to go ahead and get into it. So first thing we do is we draw the element. So in this case, I'm not going to draw it like a box here because it's on a ramp. I'm going to draw it slightly angled just to visualize, right? So this angle and this angle are the same. Um, we don't need to actually draw this part though, but I just wanted you guys to see. So first thing is I'm going to draw the weight force, and weight force always points directly downward, right? So I'm going to write it as mg, but this is also equal to weight. Mg is always pointed directly down towards the ground, even if it's angled. What this means is you're going to have to find the appropriate angles the of this vector right here, and you can use that using you can find that using sines and cosines. But for now, that is just the force acting on the box. We also have our normal force, which opposes what the box is sitting on. So the box is on the ramp. The ramp pushes back on the box this way. So we have our normal force going that way. We also know that it is in motion going this way. So we have friction opposing the motion because I never said it was a frictionless surface. So I'm going to draw friction force right there. And there you go. That is everything, all the forces interacting with our element, and that is our free body diagram. One thing to note, so notice how everything equals out and cancels out, right? So we have a force to the left being friction force. We have a force to the right, which is the x component of weight, right? We have a force pointing up, which is the normal force, and we have a force pointing down, which is the y component of the weight. So free body diagrams should always equal out. And that is one thing you can do to check. So let's go back to this example right here. Notice how the cannonball has a force going upwards, a force going downwards to counteract it, a force going to the left, and a force going to the right to counteract it. All right, let's go on to a slightly harder example. Example 2. We have a circus performer standing on a circus ball holding a 100-kilogram box over his head. I want to draw the free body diagram of the man. All right, go ahead, pause the video, try it on your own, and then I'll work it out. All right, hopefully you had enough time to work it out. Let's get right into it. So first things first is we draw our element, right? This is the person. We have the first force is, I'm going to draw weight force. So we have weight of the person going straight down. And luckily, he is not at any angle. So it's just directly downward. We have the normal force of the ball, right? The ball is pushing up onto the person while the person is pushing down onto the ball, right? So this is the weight, this is the normal force. We have nothing going to the right or left, but we have this 100-kilogram box. And right, the 100 kilograms has a weight force pushing down onto the person. So I'm going to draw that. So I'm going to draw an arrow pointing down. And this is W human. This will be weight of box pointing down, right? And although the guy is pushing the box up, we don't know, we are counting all of the person as one element, right? So we're not counting for every single muscle. If we were, we would have to draw a new free body diagram for every single muscle. But since we are drawing just for the person itself, this is our final free body diagram. Notice we have two arrows pointing down and one arrow pointing up. That is perfectly okay. Because if I was to have some numbers on them, say weight of box is 100 kilograms, say weight of human, let's say he's quite light, we'll say he's 50 kilograms. Our normal force is just equal to the ball pushing up on the person and the box. So the normal force in this case would just be 150 kilograms. And there you go. So note that they are equal. So this, checks out. And there you go. That is how you draw free body diagrams. And in the next video, I'll show you how to apply them to physics problems. Hope that helps.